Okay, so this part of our lecture is for chapter 9, and it has to do with gravitation. Newton came up with a very beautiful and simple relationship to explain a really complicated idea. Of course, he had his 3 laws, which we all know and we've learned in the fall, but he was most famous for his universal law of gravitation. And that was a relationship that he developed between objects that have mass and how far apart those objects happen to be. We know there's a lot of really complicated things that can be explained by very simple patterns and repetitive patterns. Music, for example, has a set number of notes in different octaves, but we can combine those simple musical notes into very complex patterns to create symphonies and all kinds of different sounds. We can take DNA, which is simple bases, the 4 bases that make up our DNA, G, A, C, and T. We can combine those bases in billions of different ways and create organisms of all kinds, some that live in the water, some that walk around on land, some that are single-celled, most that are multi-celled. So we can take really simple things and explain and create very complex things. The universe itself is a combination of masses that are different distances apart, and the relative motion of all those masses can be explained by this simple relationship that Newton developed and that he was helped along with by Lord Cavendish to finish the equation. What Newton realized when he was watching the apple fall was that masses will fall relative to one another, that there is a force that is exerted on one mass by another mass, and that the motion of those objects, like an apple falling down towards the earth, might be similar to the motion of the moon in relationship to the earth, or the motion of the earth in relationship to the sun, or any of the other planets in our solar system. What he found out was that there is a directly proportional relationship between 2 masses multiplied together and the force that's exerted on each other. So if we have 2 masses, 2 spherical masses, and we measure how far apart those are from their centers, and we multiply their masses together, we'll find that the product of those masses is directly proportional to the force they exert on each other. And then if we measure the distance from center to center of the 2 masses, we'll find out that the force is inversely proportional to the square of the distance. So this is something that Newton worked out on his own, this proportionality, the directly proportional relationship for masses and the inversely proportional relationship between the square of the distance and the force. It took Lord Cavendish to use a torsional balance, which is described in your book, to come up with this number right here. That number G is the gravitational constant. And what most students look at when they look at this equation, they get very nervous and they say, whoa, that's a lot of variables multiplied together with a square on the bottom. This looks complicated. When they look at the value for this constant, it's 6.67 times 10 to the negative 11, then they get even more nervous because that looks like an unfriendly number to put in your calculator. So here's the good news for my students. I am not going to have you plug numbers into this equation to calculate actual forces between planets and objects on the earth. I'm just not going to do it. So what I'm going to ask you to do is tell me how changes to the m's and the d will affect the gravitational force. So let's do an example. I have 2 masses. Let me put my pen down. I have 2 masses and they're a certain distance apart. And I would like to know how the force between them would change if I doubled their distance apart. That's what I'm going to ask you to do. We'll say they started here. Now we're going to double the distance. How is their force of attraction going to change? So let's do that as an example. If you're looking to do proportional changes, the rule of ones is the best way to make this happen. So all you do is you plug in a 1 for everything that doesn't change. So our constant G doesn't change. Our masses are not going to change. We're going to keep those the same. So everything on the top is going to be a 1. And on the bottom, we're going to have our distance is going to be doubled. So it's going to be 2 times what it was before. And we're going to square that. That means, I dropped my pen, hang on. That means that our new force of gravitational attraction is going to be 1/4 what it was before. So when we double the distance, it's not just going to half the force like a normal inversely proportional relationship would. Since we square that distance, it's going to end up being the inverse square of proportionality. So this is an inverse square law, meaning whatever you do to distance, you have to square it and put it underneath that fraction. So that would be 1/4 our old gravitational force. If you were going to change the masses, let's say that I went to a mass that was half as much as it was before. So my lacrosse ball I had was kind of heavy. This one's not as heavy. Let's say that I just changed the mass of the ball and I want to compare and see what's going to happen to the force between the two. So again, my G, the constant, is not going to change, so I'll plug in a 1 for that. One of the masses stayed the same, so I'll keep a 1 for that. The other mass became half. So distance stayed the same. So we'll put a 1 in for the distance. And that means that our force is going to be half of what it was, because we only halved one of the masses. If you were to change both masses, you just put a number in for both masses. If you were to change a mass and the distance, you just plug whatever changes you're making to the equation in and then figure out what the proportional change will be in the gravitational force. You will get practice with this on your Unit 5 problem practice page, and I have a video working that out. So you'll be able to sort that out, get a little practice. Let's talk about this force between these two objects that have a different mass. Let's pretend that this is the Earth and this is the Moon. The Earth is more massive than the Moon. They're really far apart. But do they have a different force on each other? Can the Earth, because it's more massive, pull harder on the Moon than the Moon can pull on the Earth? Or are they the same? Newton's third law says that the Moon can't pull on the Earth any harder than the Earth can pull on the Moon. So this gravitational force would be the same for both the Earth and the Moon, and that goes for any other planet in the solar system. The Earth cannot pull on Mars any harder than Mars can pull on the Earth. These forces will always be equal and opposite, and that's because the masses you're looking at and the distance are the same for both planets. All right, the last thing I want to discuss with gravitation is just a little bit of a fun scenario. Mount Kilimanjaro in Africa, really big mountain. Let's say that you are standing 1 kilometer away from Mount Kilimanjaro and you notice the moon up in the sky above you. Did you know that if you plugged in your mass and the mass of the mountain and the distance between you, and you found the gravitational force, that it would be equal to the gravitational force between you and the moon? So the moon pulling on you would be the same force as the mountain pulling on you. I'm going to just erase my 1 kilometer. So what's going on there? If gravitational force is only attractive and it can only pull on things, then how is it possible that the moon and that mountain are going to have an equal and opposite force on you? And why is it then that you wouldn't somehow be magically suspended in space 1 kilometer above this mountain, stuck in between the moon and Mount Kilimanjaro? Any ideas? Well, there's one big thing getting in the way of you being stuck in space between the moon and this mountain, and that is the Earth. The Earth is very, very massive. And it has a lot more mass in it than the mountain does. And the mountain's part of the Earth, so, you know, it's all the same thing. Your attraction for the mass of the Earth is much greater than the moon's attraction for you. That doesn't mean the moon isn't attracting you in some way, shape, or form. The Earth, because it's massive, has this really huge gravitational field, excuse me, I'm going to draw it the other way, that is pulling things towards it. And the moon also has a gravitational field pulling things towards it. It's just not as big because the moon isn't quite as massive as the Earth. And it's also so much further away from us. But does the gravity ever go away? If you move away from the surface of the Earth and you climb up to the top of Mount Kilimanjaro, you would have just the slightly less amount of gravitational force acting on you at the top of the mountain than you do at sea level, because you're a little further away from the center of the Earth, where we say the Earth's mass is located. So the mass itself is attractive, which is what brought the universe together to begin with. That is what Newton's universal law of gravitation describes. It also describes, by putting that d squared on the bottom, we're saying that it doesn't matter how far away you go from an object, there's still going to be a very tiny amount of gravitational force acting on it. So why is it then that you can have astronauts orbiting on some space station out here in space going around the Earth, and we describe them as weightless? Or do we say that gravity doesn't exist there? What is it that we say? The book has a lot of questions for you that I assigned some of for your homework to get you to think about that. We see people floating in space stations. They post themselves on YouTube all the time now, live feeds from space, from the ISS. They appear to be floating and in a gravity-free environment. But are they really in a gravity-free environment, or are they just floating around the Earth in a way that makes them feel weightless? I'm going to go take care of that phone call and finish talking about projectiles.